this thing on? Oh. Okay. I have a whiteboard. I have a King's College hoodie. I have a pen. So I'm going to prove the fundamental theorem of algebra, sort of. I'm going to sort of recount the proof that my lecturer gave me a few days ago. Now, for those who don't know, the fundamental theorem of algebra says that for any polynomial, p of x, which is equal to a n x to the n plus dot 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 plus a1 x plus a naught, that is to say it is equal to the sum to n from r equals 1 of from r equals 0 to of ar x to the r, where ar is in the domain of complex numbers. The fundamental theorem of algebra says that there exists z in the domain of complex numbers such that p of z equals 0. And the proof I'm going to give is by contradiction. So first we are going to choose some z in the domain of complex numbers which minimizes the absolute value of p of z. So choose z to minimize absolute p of z. Right? Now this, it's important to remember, z is not a variable here. It is just a number now in this proof. It is like I or whatever, square root of 2 plus pi I. Like, it doesn't matter. And so therefore p of z is also a number now. It is a constant. It is a complex constant, but it is just a constant. Now, if the absolute value of p of z equals 0, we are done. But if the absolute value of p of z does not equal 0, then we consider p of z plus h. And for now, h is just an arbitrary complex variable. Now, p of z of h is equal to the sum to n from r equals 0 of a r z plus h to the r, which when you expand that z plus h to the r, you get z to the r plus r choose 1 z to the r minus 1 h, r choose 2 z to the r minus 2 h squared, etc., etc., etc. But because z is a constant, what we basically get is a large, expanded, messy polynomial in h. So what we get is, obviously, for every single z plus h to the r, you just have z to the r. So we have a0 plus a1 z plus a2 z squared plus blah, blah, blah. So we have p of z. But then we also have b1 of h to the power of 1 plus b2 h to the power of 2 plus dot 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 plus bn h to the power of n. That is to say, it is equal to p of z plus the sum to n from r equals 0, so from r equals 1, because the constant is unchanged, br h to the r. That's this thing. And that is cool. You can calculate b if you want to. b1 is p prime of z, b2 is p double prime of z over 2, b3 is p triple prime of z over 3 factorial, so 6, and so on and so forth up until p n z over n factorial. It's like, you could do the math if you wanted. It's kind of boring though. Now, and then we create another variable, L, and we let L be equal to the minimum value of the set of j in the domain of natural numbers where bj does not equal 0. So, if b of 1 is 0, then you have p of z plus 0 plus b of 2 h squared plus blah blah blah. Then it moves on to the next one. If b of 2 is 0, it moves on to the next one. And it just takes the minimum b and takes that number. So if it's b3 that's the minimum b, it takes 3, etc. Now we know that an in p of z isn't 0, because otherwise you reframe the whole polynomial to have a of n minus 1 be the new a of n, and you shift everything over a bit. So at the very least, at a of n z plus h to the n, we have b of n is equal to a of n, which isn't equal to 0. So therefore, L is well defined. Right. Now, we're going to introduce a new variable, q. Sorry, not a new variable, a new function, q of h. And we're going to say that this is p of z, that constant, plus b subscript L, h to the L. So it's just the minimum value. We've lobbed off all of the maximal bits. To give a concrete example, I'm just going to write out a very small polynomial. Say p of z is equal to z squared plus 2z plus 3. Well then p of z plus h is equal to z plus h squared plus 2z plus h plus 3, which is equal to z squared plus 2zh plus h squared plus 2z plus 2h plus 3, which is equal to z squared plus 2z plus 3 in big brackets plus h squared plus 2z plus 2h. So if you want to, you can pause the video and figure out that that's yes true. So this bit here is that's p of z, and it's minimized, and it's not 0, so it's some value that isn't. So it is some number, and this is all real, but z takes complex value, and then we also have h squared plus 2z plus 2h. So the L in this instance would take the value of 1, because b1 is a non-zero, unless the minimal value of z in here is minus 2, in which case it would go on to 2, but that's sort of the point. What we do with q is that we lop off the bigger bit, and we're just left with the smallest h and p. So, I'm going to rub out all that crap. So we have this. Now, we're going to define R. So let R be in the domain of real numbers. R is greater than 0. And such that, and I say such that, it's going to be small enough that it satisfies 2 of the following conditions. The absolute value of b of L times r to the power of L is less than 1/2 of the absolute value of p of z. So, this minimized value of p of z, divide it by 2, and then create an r small enough that r to the L times the absolute value of b of L is smaller than it, which is very easy to do. If you take both sides, divide them both by the absolute value of b of L, then you have r to the power of L is less than absolute p of z over 2 absolute b of L. Take the log in base r of both, the natural log of both sides. So L log r is less than log of this big thing up here. And then divide it by L, log of r is less than this, blah blah blah. You can do powers and exponents or whatever, but if you really wanted to, you could just say it's, because L is at least 1, if you make R equal to that divided by 4, or whatever, like it's very, very easy to make a number small enough to satisfy that. So there does exist some number like that. And then the second condition that R has to satisfy is that the absolute value of B of L plus 1 times R plus the absolute value of B of L plus 2 times R squared plus dot 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 plus the absolute value of B of N, so all the way to the end, R to the power of N minus L. So you're just sort of adding up these R's here along as you take the increasing values of L up until B of N, where you have missed off the first L, but have N minus L exponents. Make that value less than 1/2 of the absolute value of B of L. So again, fairly easy to do because this is a big polynomial in R, and when you get very, very small numbers, like a trillionth or whatever, you can just make R arbitrarily small and make it satisfy both these conditions. Very easy, like these numbers exist. Now, H, our like variable, we are going to say is a circle of center P of Z. Sorry, it is, H is the values which have the complex values which have absolute value R. So H is equal, capital H is going to be the set of H. So it's H in the domain of complex numbers such that absolute H equals R. Right? Now, Q of H, as H whizzes round this circle, like it satisfies this circle of values that it could have, Q of H up here is going to whiz around this another circle of center PZ, because you add P of Z in, the minimized value P of Z, is going to whiz around that circle L times, because you have H to the power of L. So, you know, if you're going from e to the I0 to e to the 2 pi I, and you raise that to the power of L, and L is like 4 or whatever, then it's going to go around 4 times. And it's going to have radius B of L R to the L. So, because obviously you could write H as R e to the I theta. So absolute value B of L R to the power of L. And by this first property of R, we can choose an H so that the absolute value of Q of H is equal to the absolute value of P of Z minus the absolute value of B of L R to the power of L. So let me just write that out. Minus BL R to the power of L. Right, and I'm going to explain that in a little bit more depth. So this here is going to be smaller than 1/2 of this. So this is some positive number, and Q of H I guess the best way to imagine it is in vector space. So H to the power of L is just a direction, and you can point it towards the origin, basically. So you take your axes, your Argand diagram, I think, and this is P of Z, and this is the circle that Q of H occupies, and you just sort of pick the point over here, and so you have the absolute value of Q of H being equal to the absolute value of P of Z, subtract this vector that you removed backwards. So you can pick something that satisfies that. The other thing that you can create using the other attribute of R is that the absolute value of P of Z plus H is less than or equal to Q of H plus absolute value of B of L R to the L over 2. Now, that's because this half b to the L is bigger than this entire segment. So, and P of Z plus H is basically this segment, sort of. Q of H is this P of Z. So, this argument here, the B of L, absolute value, R to the L divided by 2, it's a value that you can construct that satisfies that equation because that is by the second property. Now, Q of H plus absolute B of L R to the L over 2 is strictly bigger than the absolute value of P of Z, because this P of Z is Q of H, subtract this here, which is, so it's much the same thing. But P of Z plus H is the minimized absolute value of the polynomial P. So it's a contradiction that this P of Z is bigger than this P of Z plus H, which means that this is actually the minimized value. And then you repeat the process over and over again. You drag the complex number Z closer and closer to the origin 0, and so we can see that there does exist this value Z in the complex, a complex value of Z for which P of Z equals 0, and then you factorize that out, and you can do the same for more and more polynomials. I kind of lost the plot right at the end there, but hopefully you could sort of keep up. I know I couldn't. That's the fundamental theorem of algebra.